very much. So I welcome all the participants. So today in this lecture, I'll try to introduce you to the basic concepts of machine learning. I'll also try to show you some of the coding part of it as well, the hands-on tutorial, like not exactly hands-on because you won't be doing it, but at least I'll show you some of the blocks and you can see how easy or difficult it can be for someone who is new to the machine learning to work with it. So let's start. So the very first thing, whenever like we are hearing about AI too much these days, right? Everybody is talking about AI, artificial intelligence, machine learning. What exactly is it? What is the first thing that comes to your mind? At least when I first heard about it, the it was mostly my perception from the movies, be it the Terminator or some animations or other, where I saw some robots taking over the world. So that was my concept of AI long back when I started this journey. But these days, we see AI in almost every application. We see that the AI is being used for social good. It is being used to tackle some of the biggest problems of the world. We see its use in the healthcare, in the agriculture. In the agriculture, we see it is being used for the pest detection, for plant health monitoring, for its different monitoring of different growth stages. In the healthcare, we see that it is being used for early detection of certain ailments or to improve the decision making, to help doctors or to help in the treatment, and also a lot of associated care with it. Then you might have seen the smart watches and the Fitbit kind of the devices, the wearable devices that we have these days. And behind everything, there is AI. There is AI which is sort of guiding us. So if I talk about what is AI, the formal definition in the sense, then we can just say that it is broadly understood as any kind of artificial computational system that shows intelligent behavior, which is complex behavior that is conducive to reaching goals. So when we talk about this, we do not like restrict intelligence to what would require intelligence if it is done by humans, right? Like humans may do a same task in a completely different way. We do not expect that from the AI to perform it in the similar manner. So that also mean that the mostly we talk about the technical AI that may show only the limited abilities in learning or reasoning, but they are good or they can excel at automation of the particular task, right? So generally, when we talk about AI, there are mostly we say there are three stages of AI or three different types of AI. That is narrow AI, general AI, super AI, right? So whenever you hear about machine learning AI around you, like you use, all of us use Gmails, right? We There is a spam folder or where all the emails which are tagged as spam, they go over there. So there is an algorithm that is working behind it. Now the thing is, the algorithm which is good to classify between spam and non-spam emails, that can the same algorithm be used for some other task? Can the same algorithm be used for, let's say, I don't know, classification of cats and dogs images? Maybe not, right? Those parts, they are dedicated to assist with a very specific task. They are good at doing one task. For example, we keep hearing about all of these like chess or go that AI has uh, sorry, yeah, that the AI has beaten over the world champions. But that's something that we need to understand. That AI, it lacks generability. It doesn't have the generalization capability. It is similar to the purpose. For example, that we see bees or we see birds who are very good at making nests, or the bees who are very good at collecting the honey. But can they switch over these jobs? No, they cannot, right? They are good at a specific task, and this is what the purpose of narrow AI has been. And that is something that we have around us almost everywhere these days. So we are mostly in the domain of the narrow AI. But the recent but and the most important characteristics, or something that we aim to target, that is a generalization ability. So as I was saying, that the current AI algorithms, they are superior to superior in performance than humans only in a particular domain or in a very restricted task. But in terms of, we want general AI where we can take knowledge from one domain and transfer it to the another domain as well. Some AI which is performance, like performance wise, it is like as good as, if not as good as, like maybe equivalent to humans in perception task, and it is capable of reasoning. This is something that we want to reach. Now the third stage is the super AI, where the machines that are an order of magnitude smarter than humans, which is, you can say that AI as performant as all humans combined. So this is a very, you can say that a far-fetched future for us, something that we envision to achieve maybe uh, in coming years, but that's not the stage where we are at right now. Right now we are just in the stage of the narrow AI. So whenever I'll talk about machine learning or AI, I'll be mostly talking about that only. So if I sort of categorize, like what is AI, what is machine learning, what is deep learning, we keep hearing all these words, like especially deep learning these days, it is such a buzzword. Everybody wants to use deep learning, right? So AI, you can say that it is a broader perspective. AI is something which where we try to simulate human intelligence. It is a broader. It consists of narrow AI, where we can perform the specific task, and then the general AI and the super AI, as I talked about. And in the narrow AI itself, a part of it is what we call as machine learning. Machine learning, which learns on the past data. This is what we will be talking about today itself. You can say that machine learning, it is a process by which computer is able to perform specific tasks without using any explicit instructions. It tries to look into the statistical patterns which are found in the past data. So like as I was saying, that algorithm to classify a spam and a non-spam email, or an algorithm to classify, let's say, cats and dogs, right? So which can automatically tells us if the cat ears, they are pointy, or the dogs, they have different sort of ears. So that's what is machine learning, where we try to learn from the data that we already have, and then try to predict what it will be, try to predict on the unknown samples. So, and a particular part of uh, machine learning that these days we really work with, that is called as deep learning. It is a very particular learning structure, you can say. Like earlier, like in the beginning, we had, the rest of the algorithm, sometimes we call as shallow learning as well. For example, the decision trees or the linear regressions. So deep learning is something where we have deep neural networks with many hidden layers. So we will not go into the details of deep learning at this stage, but this is something which is happening now, the narrow AI part. And this is something that we hope to achieve in the future, the general AI and the super AI, to have the capabilities either equivalent to or greater than the humans. So before we dive more into the basics of the machine learning, it is important for us to understand a bit of the history of the AI, how it started. So the very first time the AI term was used, it was around 1950, 19, somewhere around 1950, 19, I think it's 1956, the Dartmouth conference. So during this time period, from, right, yeah, so it was during during this conference that first time the AI term was coined. And it was also a very good period from around 1950 to 1975, where there was a lot of hype that the AI will change the world. Then came the time period of AI winter, where almost there was not a lot of enthusiasm. Then again there were new hopes when the systems like expert systems came into the being. Then again came the time period of AI winter, we call it the AI winter too. Now if I talk about, like, after around, you can say, 1990s, 1999, we have seen a lot of explosion in the growth of AI. Like, in fact, in the terms of investment, in the terms of research, there are a lot of resources which are coming up. In fact, it has grown so much. We are even talking about the explosive growth. We're talking about the fourth industrial revolution. And there are also reasons. There are mostly three main factors which has resulted in it. We will just talk about it in the next slide. And around these days, in fact, around now 2020, we have even like started thinking about the implications or the concerns which are related to AI, in the sense of the what should be the regulations, that the AI is it being used ethically or not. So that's the stage where we have reached right now. So as I was saying that, these days the AI has taken up because of three major reasons. One is very first one is bigger data. If you will just look around you, right, you use all your social media platforms. You have Facebook, you have Google, you have your Instagrams, where the data is being generated in the form of text, in the form of videos, images, and the scale at which it is being generated, it is something that we had never imagined before. So we had access to a bigger and a bigger data set every day, with more and more wearable devices, with IoT devices, with the automation of homes, Alexas and Siris everywhere around us. So that's the one reason. That is the availability of more and more data. The another reason is the improvement in the computational resources. Now, earlier, if you will remember, the kind of memories or the kind of processes that we had, and the difference that you will see, even your mobile phone is much more computationally powerful in comparison to the computers or the that we had long time back, right? So we have access to better computational resources. We have access to GPUs, and it is just available at the at the click of the mouse. We also have these days resources like cloud computing. Then we have something like these big companies coming up with their servers and everything. We have AWS. So there's a lot of computational resources which are now available due to the advancements in the chip development and everything. Now, the third reason is better models. Now, we also have better models, like we were talking about the deep neural nets. They have also improved over the period of time. And these three reasons have contributed a lot to the explosion in, I'll say, in the growth of AI and the machine learning. So, we will focus on at least for this lecture, a very specific part of what the machine learning is and how we can develop our own algorithms. So again, firstly, going by the definition. So it is said it is a field of study that gives computer the ability to learn without being explicitly programmed, right? And if I try to describe it in the form of a certain parameters, we will describe it by three parameters. That is P, T, and E, where P is the performance measure, T is the task, and E is the experience. Now, what does this really mean? Task is something that you want to achieve. Task is something that you want your machine learning algorithms to do. For example, I talked about spam or non-spam emails. So here the task will be that you classify between the spam and the non-spam emails. Now the performance measure is which tells you how well your algorithm is performing. Performance measure you take into account to improve your algorithm over the period of time as well. For example, again, if I talk about spam and non-spam emails, it will be how many emails you have classified correctly. How many emails which were spam, our algorithm has also tagged it as a spam. And now the third part is the experience. What is the meaning of this experience? Like humans, we learn from our experience, right? Let's say we touch a hot pan and we burn our finger or something, then our brain learns not to touch the hot thing. So that's the experience that we get, and that's how our brain learns it. Similarly is with the machine learning algorithms as well, based on certain experience, which in this case is generally a database which tells us, let's say if it's classification between cats and dogs, database which tells us that this particular set of images are cats and this particular set of images are dogs. That's what we mean by experience here. So in general, now we have been talking about, like, we have done a lot of programming in general, right? So how it is different from the traditional programming, how machine learning is different. So if you look here, in the traditional programming, we have certain input, we have a program, and then we get a certain output. What does it mean? For example, our inputs here are two numbers, two integers, 2 and 3. Our program tell us that we need to perform an addition function over it. Then what will be our output? It will be 5, right? Now the way machine learning works is it is different. You have input and you also know your output. Here the purpose is you need to find out what is the relationship between this and between your input and your output. Like what is the program which is supposed to be there. For example, if we have input as 2 and 3 and output as 5, so the machine learning algorithms, it will try to understand if the relationship between them, it is a function of addition, it is a function of multiplication, or some complex mathematical function over there. So this is what the machine learning is, and this is how it is different from the traditional programming, where it's not just about the explicit coding, explicit instructions that you tell, it is also how it learns, it tries to find out the patterns from the given data, right? So now the next question is, when do we really need to use machine learning? Is it like applicable everywhere? Can we just use it on almost every other task? For example, I'll give you a very simple example, and you tell me if it requires machine learning or not. Let's say you have a vending machine, right? And the purpose of the machine is to, okay, not a vending machine, maybe just a counter. You have a couple of coins and you need to build a device that will count how many coins have been put in there. So what do you think? Is it a machine learning problem or is it not a machine learning problem? Anybody can answer. If you want, you can also like write in the chat or something, but I'll prefer if you will speak. The reason being, I'm not able to, while I'm sharing the screen, I'm not able to see the chat.
No, ma'am, it is not a machine learning problem.
Hmm. You are,
Because I am Archana.
yeah, Hanji Archana. I'm so glad that you are here. Yeah.
Thank you, ma'am. I think it is not a machine learning problem because counting of coin is only it requires a sensor which sense and then it a simple programming is required to count.
You're absolutely right. You're absolutely right. This does not require
Just
any.
like a micro, I think by using microprocessor or microcontroller, we can perform this task.
Yeah, exactly. Now, if I tell you, let's say that you have two different type of coins. You have a 5 rupee coin and a 1 rupee coin. So can that be a machine learning task? So that will require that may or may not actually require machine learning, to be honest. So you can use, let's say, a camera to see if the images on it, like what is inscribed on the coin, that differentiates the 1 rupee coin from the 5 rupee coin. Or you can use maybe a weighing machine that tells us if this is the 1 or this is the 5 rupee coin. But that's a task that may still need machine learning, right? But all of the tasks do not. So when do we use machine learning? There are couple of different scenarios. The one where human expertise does not exist. For example, navigating on Mars, right? So we are familiar with the rovers. It's completely unknown domain, a completely different terrain where humans cannot even reach. So there we need to impart some sort of intelligence to the bots, to the rovers which are out there, because human expertise does not exist there. Similarly, the second domain where we require is where humans can't explain their expertise. For example, speech recognition, or even the language translation. Sometime there are a lot of cases where we just know how to do things, but we cannot just describe how. For example, let's say. When we recognize the what others are speaking, this is something we learn from the childhood itself. A kid doesn't need to we don't need to teach the exact, the grammatical rules to the kids to teach him or her the language. They learn from it, their parents, they learn it from their environment. They may not know what are the rules, if a, an or the should be used with it, but they know that this is how it should be. So there are many cases where we just cannot even tell that how we are able to perform it, where we cannot explain our own expertise, right? So that's the second scenario. The third is where we need a lot of models to be customized. For example, these days we have the personalized medicine, right? We want that the rules should not be one medicine for all, depending upon the type of diseases, maybe the depending upon the type of genetics that somebody has, or depending upon the kind of the nutrition, the health, the lifestyle, we would like to provide the certain medicine, and it is not possible to do it for a doctor or for one person to customize it for everybody. So that's where we need the machine learning models to assist us. The third is where the models are based on, sorry, the fourth one, where the models are based on huge amount of data. For example, these days in the genomics, or even in the case of the IoT devices that we have, there is so much of data that is being generated that it is humanly impossible for someone to go through it and make sense out of it. So we need machine learning algorithms for that kind of purpose as well, where we can look, where the algorithms can help us to understand what are the patterns, what are the trends which are visible from the data. So I'll be sharing some of the machine learning examples here. So this is actually one of the few examples where machine learning was really used. So if you will see, this is there are some handwritten digits, and the task is to recognize those handwritten digits, right? And these digits are written by the human. So if you will see, it is very hard to say what makes a two. Like all of these examples, these are a part of two. It is even difficult for humans to say that which one is two. Like this one, I cannot identify. I may guess it as seven as well, right? So, so these are the kind of examples. These were the kind of tasks which helped us to develop the machine learning algorithms and grow on top of it. And this is a very typical, I'll say, a textbook problem, or the problem where everybody starts learning the the ML algorithms itself. Now, there are many other examples from our daily life. I have already talked about spam, non spam, or the spam and the ham emails. Then we use Google Translation all the time, where we translate from one language to the another. These days, it has improved quite a lot. So, so that's the another task where we see the role of machine learning. And then, these days when we write in the search engine, we have this autofill options. For example, here I have an example of Priyanka Chopra is, then it automatically gives me certain set of options from which state Priyanka Chopra is, Miss World, Priyanka Chopra isn't romantic. So this is another example where the backend, like behind the machine learning, is being used. And then the fourth, we all watch Netflix, right? Netflix, Hotstar, or Amazon Prime. So we watch one movie, it tells us hundreds of other movies that we should be watching. It may not be very good for health, but it does recommend us a lot of options based on what we have liked before, what we have watched before. So based on our prior preferences, it tries us to recommend what we will like in the future as well, or what we will like to watch next. And you will see that it keeps in the beginning it may not work very well. In the beginning it may give you some random recommendations as well, but with time, as you keep on watching more and more, it learns more about your behavior, your choices. It will also give you the better recommendations as well. So machine learning, it is not very far fetched. We see it around us. It is also being used in a lot of automation and the manufacturing setup as well. Like I have already talked about the example of the games, right? Where we look into the, like the Google DeepMind, where there was the game of the AlphaGo, where AI machine learning algorithms won over the world champion. So and how did it do that? It learned from millions of, like, if not mean thousands of the previous games, looking at all the moves that people have done. It learned from there, and then finally able to beat the humans as well. But again, this is an example of a narrow AI. Then we have all looked at those videos by Boston Dynamics, where we see the bots moving around, and it also looks very scary. Then we see the AI in the automation where it is being used in the manufacturing setup. Then we know that in the countries in the developed worlds, we now have at least a semi-automatic, semi-autonomous, or the self-driving cars as well, which are laden with different type of sensors, be it the obstacle detection, be it the your lidar, your cameras, and it also it controls the cars as well. So the machine learning AI, it is not very far fetched. In fact, I'll say the most interesting example where it is being used, it is the biological data. Like we all are made of our DNA, right? And this is something that uh, maybe describe a lot of our behavior also, how like our genes a lot of times determines the kind of diseases that we are going to have or the kind of health we will have. So we say that DNA, it is a storehouse of the genetic information, and by now we have only decoded, you can say, 2% of the human genome codes for protein. And I will maybe not go into the details of this. So the purpose here is to understand the scale of problem we have, the kind of data sets that we are dealing with. So in humans, the DNA molecule in a cell, it is said if we fully extend it, it would have a total length of 1.7 meter. And if we unwrap all the DNA that you have in your cells, you could reach the moon about 6,000 times. So that's the kind of data that we are dealing with here. That's the kind of data that the humans cannot go through in this manually. So we need to have machine learning algorithms, we need to have computational capabilities there. And we have also seen that it has improved significantly over time. Now, this is something which has been predicted by the Moore's law. It tells us that with time, what kind of investment we would require, or the cost. This is a very specific example for the cost per genome. Tells us what kind of cost we would require for the uh, for, I'm sorry. Per genome. So you can see that we have surpassed beyond our expectations. This is what we expected. We expected that the pace will be like this, but this is where we are. The cost has decreased so much, and that it is actually now feasible to do it. It is actually happening, even like the you can send your saliva or your information, and they can decode it, and they can tell you what all possible what kind of genetic information is there, what kind of possible disease you can have. So now let's say we have, now the question is, let's say we have enough data about, here we have the example of Alia Bhatt. We know its demographic information, that she's a female, 26 years old. We have her information about, let's say, her medical imaging, her medical signals. Then we have her clinical data, we have her genetic data. Now, based on this, can we sort of predict what sort of diseases Alia Bhatt will have, or how long maybe Alia Bhatt will live? The answer to this could be that maybe yes, it's not that far fetched for us. So the important thing is how it is different, how it is different from the basic biology itself, right? And how we use it. Can we see that which kind of patients are more susceptible to certain risks? Now we saw that in the times of COVID itself, the data told us that maybe the elderly people are more susceptible to it. They are the ones who needs to be protected. Then the people who had comorbidities. So can we find out who are at risk patients, who are at risk of developing cancer or the different diseases itself? What are the environmental or the genetic factors? Can we develop drugs to target defective genes, discover a new antibiotic itself, right? So this is where we can say that the machine learning also meets biology. It is the example of the personalized medicine, where we look at all the genetic information and try to see if the diagnostic uh, with our test positive, they are likely to be benefit from a certain treatment. I'm sorry. Yeah, and test negative who are unresponsive to the certain therapy. And as I was saying, this is something which is happening now. There are already companies which are doing it. For example, there is a company called 23andMe. They try to estimate your genetic chances of getting your type 2 diabetes, if it is as low as, let's say, 8% or as high as 52%. So it will tell you on the basis of your genetic information how much of risk you are at. Now, after all of these examples from the different domains where the machine learning is being used, now we will go a bit more technical into what is the machine learning pipeline in itself, right? So as I was saying, whenever we define a machine learning task, we have three different parameters, you can say, or the three different things that we need to remember or keep in mind. First is, what is your task team? Then what is the performance metrics be, and what is the experience? So again, we will come to some of the examples. For example, the first one, recognizing handwritten words. We saw that example where it was very difficult to identify what was 2 or what was 7. So in this case, the task is this one. Now, what is the performance measure? The performance measure will be the percentage of words correctly classified, and it will be done on the basis of the database of human labeled images of the handwritten words. So these are the three things. Similarly, let's say if I talk about, let's say we have images, images of the some MRI or some other images, and we want to see if the tumor is benign or malignant, right? If some person has cancer or not. So that is the task, and the performance measure will be the percentage of tumors correctly classified, and the experience will be the database of the patients that you previously have. So in the case of machine learning design, what we have is we generally take some training examples, some database. For example, if I need to know if a customer, we need to approve the loan of a certain customer. So we have certain sort of records of the credit records of the customers, right? Like previously, what was its behavior? Then we have, let's say, a certain learning algorithm, and there is a certain unknown task, like which you can say that the ideal credit approval function, if the customer has behaved this way, this is something that we need to achieve, this is something that we want to figure out. In order to figure this thing out, we develop our learning algorithm, which gives us a certain set of hypotheses, certain set of candidate formulas, you can say, and we fine tune one, we find one final hypothesis which may be the best approximation to our unknown target function, which gives us the minimum error in general, if we say. So this is in general the machine learning design. And there are generally a few steps that we follow whenever we get certain data set, we have to apply machine learning. The very first thing that we do is looking at the big picture, like what is the task at the hand. Then there is data collection. We'll go into the data visualization, then we see if we can gain some insights into it from the way of the data discovery. Then we look into how we do the pre-processing, the data preparation for machine learning algorithms. Then there's model selection, training, fine-tuning the model, solution representation, and finally launch, monitor, and maintain your system. So we will talk about all of these steps. In fact, I'll show you an example of a data set, and we will follow it along through the actual coding itself, that what are all these steps and how we need to go through it. So this is the example that we will be looking at. Now this is called a you can say that this is a problem of predicting the prices of the certain houses. So we have a data set which tells us where the houses, like the homes, they are located. It tells us other information, for example, how many bedrooms are there, how what is the size of the house, where the house is located, what is maybe the income of the people who are staying there, or the in general the average income of the neighborhood who are staying there. And based on that information, we want to predict what will be the price of the house, right? So this is the example. So now what is the bigger picture here? Now that's our first step. The bigger picture here is, first we identify the task as hand. So that means that we have a data which has matrices such as population, median income, the housing prices, the median housing prices in that area, and so on for each block group. And this specifically, the data set that we have, this is for California. right? So this is your task. Now, what model should be able to learn from this data set? Should be able to predict the housing price given all the other matrices. Now, how we frame this problem? The one, like if we are developing, there has to be a certain end goal to it, right? A certain business model to it. So the primary objective could be building the model, but this is not the end goal. Once we build the model, the end goal could be how does the company expect to use and benefit from this model. And this is important because this will help you to frame your problem. This will help you to select what kind of algorithms you have, what kind of performance measure you will choose, and also how much of effort you should be spending, right? And it is also possible that sometimes we use one model, take its output, and then feed it to another algorithm. Use that as a signal to the another task. So there could be a downstream system that will determine whether it is worth investing in this particular problem or not, right? And then there could be another objective as well. That is, we need to beat the manual or the rule based, like a certain performance that we already have, like how this will perform better than, let's say, a regular real estate agent. If a real estate agent tells you that this should be the price, is he doing a better job or is your algorithm doing the better job? So what we need to beat, is it another previous knowledge, is it a human, is it another algorithm that has been used previously, either based on the certain set of rules or the ML algorithm? That we also need to understand before we dive into doing all of this, right? So as I was talking about the business pipeline, uh, in this case, for this particular problem, it will be that we have certain upstream components, in the sense of what are the different features of the house. We get data from the district which will tell us about the pricing in the district, right? This is further fed into the district prices, which is used further for the investment analysis along with certain other signals. And you can see that what kind of investments you would like to do. So there could be a certain business pipeline. This is one of the examples of the business pipeline that could be there. Now, the second thing is, after you looked into what exactly your problem is, right? What is it that you want to achieve? Now, how do we frame it in the sense of a machine learning problem? Now, it could be a supervised, unsupervised, a reinforcement sort of a problem. It could be a classification, regression, or the batch learning, or the online learning techniques. So, we will talk about all of these. So, when I firstly talk about supervised learning, now, what does this really mean is that we have a certain set of known data and we also know its response. For example, the very beginning I showed that, we have input 2 and 3 and the output is 5, and we need to figure out what the relationship will be. So we have the input as well as we have a certain output corresponding to it. So that's what make it a supervised learning. In the sense, you can see that there is somebody who is supervising you, right? Somebody who is telling you what is right. If you're predicting something, they'll tell you, no, this is not right. We already know what the answer should be corresponding to this particular input. So if I take an example, so any of you, do you watch Star Trek or Star Wars movies? Like, I'm a big fan, so I've put an example of the Star Trek and Star Wars. I know there are a lot of people who will fight over which one is better, but I like both equally. So let's say I have certain, characters from the Star Trek. I have Spock and everybody, certain set of, and similarly, I have certain set of characters from the Star Wars, and we know that this is Star Wars characters and these are Star Trek characters. This information we have. On the basis of this information, we build our model, we train our model, and then when a new data comes, then we try to predict, will it be a Star Trek or will it be a Star Wars model? Now, this is a very clear example of supervised learning where we had the output label as well. Now, let's look at its counterpart, which is the unsupervised learning, where we do not know what the output is corresponding to that. So, now going by the similar sort of example, I have again put a lot of characters here, but now we do not know if this is a Star Wars or a Star Trek. Or a Star Trek character, right? We have no idea about its output. So that's what we have in uncategorized data, and that's what make it unsupervised in nature. So our task here is, can we find maybe the certain clusters? Can we look at certain patterns in here which will help us to say that, okay, whatever features we have, that these characters, they look more similar to each other, or they form one group, and these characters, they form a different group. So this kind of learning, this is called the unsupervised, where we do not have a label data. And there are certain set of examples for unsupervised, for example, clustering, principal component analysis. Similarly, for supervised, we have linear regression, we have logistic regression. So again, now going a little more deeper into it, when we talk about supervised, now further, there could be two different type of supervised learning models as well. The one could be a regression example, another one could be a classification example. Now, in very short, if I try to say that, like we know that supervised learning, where we try to learn from the label training data. Now, uh, now, what kind of label data would that be? What is your output? Let's say if your output is discrete, in the sense that we have over here, we have only two outputs, Star Trek, Star Wars, right? So let's say we represent it as 0 or 1. If your output is, let's say, discrete or categorical in nature, we it may be a classification task. But if your output is continuous in nature, then it is a regression problem. Now, for example, if you will look here, we have a certain x. Based on this x, we want to predict the value of y, right? Now, sorry, just excuse me for a minute. Yeah. So based on this certain x, we want to see what is the value of phi, right? So these are the one with the red cross that you see here. These are the data points that we had, and we have tried to fit two different models. The one which is a straight line, as you can see, another one which is maybe a more curved sort of a line. So this is an example of a regression problem where your output is discrete. Now, similarly, if we have this kind of data set, let's say we have two classes, one represented by red crosses, another by purple circles, and we want to find out the line which helps us to discriminate between these two classes, that helps us to segregate, which separates these two type of data. Now that becomes a problem of classification. So mostly when we will be dealing with the machine learning algorithms, especially in the supervised learning, most of the problems, they can be classified into the regression or the classification sort of problems. Now coming to the unsupervised part of it. So in unsupervised part, as I said, we have certain data set, right? We have certain points. Our objective is, can we try to find out what is the hidden structure in that label data set? Now you will see we do not have any, we don't know if like all our we do not have any output label. They are all circles. We do not have anything marked with the red here. So we just try to look at mostly the distance based measures to look into the similarity between the data points, and how similar they are to each other and how dissimilar they are from the other data points, and then we try to cluster it. We try to maybe look at the main features of it. So this becomes the problem of unsupervised learning. Now, in this case, do not get confused by these green circles. This is something that we did not have earlier. This is something that we want to achieve, we want to get further. Now, the third type of learning is the reinforcement learning, where what we do is we sort of first observe. Let's say you have a certain agent and there is a certain environment. Now we do not again have a label data, but we know that if taking a certain action, whether we will get a reward or we will get punished for it. For example, here we have an environment where if the agent move towards maybe the left hand side, it will get burned with the fire, and if it move towards this, it will the second thing could be it could move towards the water, right? So the very first thing that the agent does is observe the environment, and then select action using the policy. Let's say it took the action of moving in this direction, then it either gets penalty or reward. In this case, it will get the penalty. So it will know that this is the action, this is the step that it should be avoided the next time. It should learn its behavior, it should update its policy and iterate until the optimal solution or the policy is found. So now this is sort of an example of the reinforcement learning, where somebody, let's say, is there with the stick and telling you, okay, like a carrot and a stick model, if you do this, this is right. Like if you're going in this direction, if it is right, you will get a carrot. If you're going in the wrong direction, then you will get a stick, and you will learn not to follow that path where you will get the stick. Now that is an example of reinforcement learning, and most of the games that we see, these are actually the example of the reinforcement learning itself. And in general, there are many different type of algorithms: a linear classifier, decision trees, neural networks. Then there are k-nearest neighbors. Today we will definitely go deeper into the linear regression maybe, but we will not have time to go into the different type of the algorithms. So this is just to give you the glimpse of some of the other algorithms which exist out there. For example, the linear, which is try to sort of separate the two classes linearly. Then there are decision trees, which try to come up with the rule based tree hierarchy sort of a problem, where it looks at what is the value of certain features. If it is greater than 20, then this will be the decision. If it is less than 20, this will be the decision. Similarly, neural networks and the other algorithms. Now this was mostly about the kind of problem, the first thing that we did, the supervised, and then the classification and the regression. Now the next that we will learn here is, will it be a batch learning, or will it be an online learning? Now what is the meaning of the batch learning? Where you have the data, like you have all the available data, and you feed all of that data to your algorithm. Like your system, it is incapable of learning incrementally, it must be trained using all the available data. But exactly, it takes a lot of time, it takes computing resources, so generally it is done offline as well. So what is that we do is, we first train the system, and then we launch it into production, and it runs without learning anymore, it just applies what it has learned. And this is an example of the offline learning. For example, we talked about cats and dogs, right? Let's say I had 10,000 images of cats and dogs, and I trained my algorithm on top of it. After I did that, I deployed it on the web, and people started putting the images of their different images of their cats and dogs, so that they can identify whether it was a cat or it was a dog. Now see, with time we are collecting more and more data, and our algorithm have an opportunity to learn from it. But in this case, we don't sort of use that opportunity, or maybe we again keep that chunk, we collect a chunk of that, and a long time later we will do that. So the another example is online learning. So what is generally done in online learning is, one, we have the data, we train the ML algorithm, we evaluate the solution, and we launch it, right? But at the same time, we get new data. We get new data on the fly. Let's say people started uploading their data itself, and your system is getting the new data all the time, right? So using that new data also, we will learn our algorithm, and we will learn and run. So it is like incremental learning. Sometimes it is also called a sequential, or the a mini batch sort of a learning, right? Where we do not maybe use the whole data altogether, but we take chunks of it. Now sometimes the problem with the online learning, what you when there is a huge amount of data, what you do in that case, if there is a lots of data, and it may not and it is going to take a lot of time to learn as well. So what we do is, we chop the data into the pieces, and into the small batches. So we train the online ML algorithm on top of it, evaluate the solution, analyze error, study the problem, and then keep on training it into those small chunks sequentially. So I mean, it has a faster learning rate, but also it forgets quickly as well. So but it is also at the same time is less sensitive. Like it gets a chance to learn and be faster in the online environment as well. So the next thing that we need to learn is, like, now we have identified what kind of task our will be. Will it be supervised, unsupervised? Will it be classification or the regression? The next is, as we talked about, that is our performance measure, which is P. Right now, how do we evaluate the accuracy of our performance of our algorithm? In case it is regression, so I will not go into details here. I will show it to you later on as well. If it, let's say in the case it is regression, we go into the root mean square sort of values. If it is classification, we'll go into the accuracies and all. So let's say in this case, when we are talking about the housing problem, right, we will keep that as our fixed problem, and we will try to solve it right from the scratch. So we know that in that case we have certain input variables and we also have an output. So it is an unsupervised problem, right? And then it is a multivariate regression. Like it is a regression problem because the output is a continuous value. We want to predict the houses, and the houses can take any, and like we want to predict the prices of the houses, and those prices can take any value, right? And it is multivariate because we have many input variables. We have the size of the house, the number of the bedrooms, the number of the bathrooms, and many other different variables. And since it is not a very big data set, maybe we'll call it a batch learning. We will take all the data set at once and we will train our algorithm on top of it. And for the performance measure, we will take the root mean square error, which is what we have predicted minus its true value, take the square out of it, sum it over all the examples, and then take the square root. That is a root mean square error. So this is a very common choice in the regression. We will discuss this in details about the especially the regression performance measure later. So for the time being, if you do not understand it very well, even that's okay. So this one was our choice for the housing data set. Now I'm giving you another data set, right? Now this is the data set where we want to find out whether the tumor is malignant or benign, right? So we have certain set of images which tells us that these tumors, these are benign, and these are the tumors which are malignant. And we want to predict on the unknown images whether this is a benign or it is malignant, right? So what sort of problem this will be? It will be again a supervised problem because our training data set has labels. Now it becomes a classification problem because we have two different classes, malignant or benign. It's not continuous, it is discrete. Then it is, let's say it is a batch learning because we get a chunk of data set, like a batch of data set, and then we will work on it. And then in terms of the performance measure, it will be classification accuracy. So we will just look into the performance measures for the classification problem itself. Let's say we had 1000 patients, right? 1000 uh, uh, most likely breast cancer patients. So out of those, I'm sorry, uh, out of those 950 have been declared free of cancer and 50 have been declared with cancer. So we have 1000 patients, out of which 950 were declared, let's say, free of cancer, and the 50 were declared with cancer. Now what happens is, out of those 950, 940 which were declared free of cancer, like the patients which we said, okay, they do not have any cancer, that was correct. They did not have any cancer. Like even their true label says that, doctors also says that. Now that becomes true negatives, like who tested negative for the cancer correctly. But the 10 patients who actually had cancer, but our algorithm declared them free of cancer incorrectly. So that becomes false negatives. So see, here we are putting positives as having cancer and negatives as free of cancer. So two classes, positive and negative, right? And five of them, they who had cancer, they were also correctly identified as having cancer. That becomes true positive, who are tested positive for cancer correctly. And then 45 normal patients who were misdiagnosed with cancer, right? Like these patients, they did not have cancer, but our algorithm told them that no, these are the patients which needs further treatment or further diagnosis, they have cancer. This is now a very, we call it false positive. This is also a very deadly case in itself, in the sense that, let's say somebody doesn't have cancer, but your algorithm tells you that no, they have cancer. They may go through the whole process of chemotherapy or the different sort of treatments, but they actually did not need it. So it is very important to even select what kind of measure is more important for you, more important to correctly identify. For example, is it more important to decrease the number of false positive, or is it more important to decrease the number of false negatives? Like as we are saying that the normal patients who were misdiagnosed with cancer, that is very dangerous situation. At the same time, the patients who had cancer but we declared them free of cancer, they may not get any treatment, right? They will think that they're going to live for a long time, but it might be too late before they realize that they actually have a cancer and they were misdiagnosed. So this becomes false negative, and this is also equally dangerous. So it becomes very important on the part of the machine learning algorithm designer as well, to understand the problem, to understand the challenges which are there, to talk with the domain experts, and to see what is the best possible solution out of there. And generally, in the classification problems, what we do is we take the total number of the correct cases divided by the total number of correct plus incorrect cases. That is how many we have correctly identified, which becomes true negative plus true positives divided by all of these: true negative, false negative, true positive, and false positives, right? So that is the accuracy, is more or less the measure that we use. But yes, if it is imbalanced data, then accuracy is not exactly a very good measure. Will not go into too much of details, that will become a different lecture on itself. So we will for the time being stick to the accuracy in itself. Now, as I was talking about that how dangerous false positive and false negatives can be, now this is the another situation where, let's say, the false positive will be equivalent to telling a man that he is pregnant, and the false negative is equivalent to telling a pregnant woman that you are not pregnant. So I mean, have to be very careful that how your algorithm, how good your algorithm is performing. So now we will go into the some of the hands-on tutorial part of it. So we will use Python Jupyter Notebook, particularly if I talk about some, and the certain libraries which are used. They are the Matplotlib, NumPy, Pandas, and these are some of the instructions. If you would like to run it by yourself at home, please feel free to do this. So now I'll take you to the codes itself. Okay, so can you still see my screen? I'm okay. Yeah. So in this case, now I'm not sure how much familiar you are with Python, but most of the machine learning algorithms that we do, especially with the deep learning coming into the picture, we use Python. More or less, because it's also open source, it's free of cost, and there are so many machine learning libraries which are already there, which are stable and robust and tested over the period of time. So this is at least my first go-to choice for developing any sort of machine learning algorithm. So in this tutorial here itself, we will be talking about the median housing price data that I talked about. So there are a few steps here that you can probably ignore for the time being. The very first thing, as I was talking about, one is first to frame your problem, right? The second is then you get your data based on how what kind of problem you have, right? So we go into the data collection process. So the data set that which I am using, I'm getting it from the GitHub. So I'm just going to run this. So this is how our data set looks like. So you will see in this data set, we have columns like longitude, latitude. It basically tells us about the location. Then we have the median age of the house, for example, how old the house is. If it is a new house, or if it is very old, it also determines its current condition, right? Then what are the total number of rooms, total number of bedrooms, the population maybe of that block or district, then the households in that block, what is the median income of the people who live in that block, and then what is the median house value. This is something that we want to predict, right? And remember, all of this data is mostly at the block level, because I think it'll be very surprising if someone will have 1100 bedrooms in their house. So this is over a block level, this is not just the per house data, right? And then there is also another information which tells us how close it is to the ocean, if it is near bay, if it is more inland. So here we have 9 input variables and one output variable, which is a median housing price. So if we look at the size of this data set, so housing dot shape lets us do it. It is around, we have 20,000, around 20,000 we have samples, you can say, the number of rows, right? So we have data corresponding to around 20,000 houses, or the mean data around that block, and the 10 number of columns, where 9 are the input variables and 1 is the output variable. And if we further look into what kind of variables are these, we will see that these are the ones which are like float in nature. This is the one which is objects. So housing.info, like housing is the variable where we have stored our data. If you will notice, we will be using this name throughout the session, like throughout this coding session. And if you will see, we have one very interesting parameter here, which is the ocean proximity. All of the variables that we have, they are, if you will see, continuous in nature, right? This is the only one which is categorical in nature. And this is the one which has these values, like 1H ocean, inland, near ocean, near bay, island, and number of rows corresponding to all of those, like how many rows have these values. So apparently there were only 5 houses which were on the island. Then there is another information that we can see, which is called housing.describe. We can look at the mean values, the standard deviation. For example, it tells us that if we talk about the total number of rooms, the minimum has come to 2, and the maximum value is around 39,000, right? And this is the mean value. So please remember, this is not corresponding to one house. Again, I no house can have 39,000 houses. I mean rooms. So that's the one thing. So this was about our data, right? So the, like, after looking into the big picture, we have the data, right? So the next step is, can we sort of you can say visualize it? Can we, after collecting the data, what other kind of insights we can get from it? So like to know more about it. So what I have done here is, I have plotted a histogram for you, histogram which tells us about the distribution of all the variables. For example, households, the median age, the latitude, longitude. What you may notice here is that most of these distributions are unimodal in nature, right? Like it increases and then it decreases at certain point, except the median, housing age, and maybe the latitude and the longitude. So what does it really tells us? What kind of insights it really provides us? Maybe it can tell us that, that some of the houses, they are around 10 to 20 years old, maybe around 15 is their age, and the another set of houses, they are very old, they are around 35, right? And similarly, the longitude, latitude sort of tells us that maybe they are concentrated on sort of two different locations. Maybe that could be one of the insights. And the another thing to notice here is that all of them, they have different scales. For example, the age varies from 0 to maybe somewhere around 55 or 60. The longitude, latitude has a different scale. The total number of bedrooms or the housing value has a different scale. So these are all the points that we need to know, because this will help us to further understand how we will pre-process our data, what kind of scaling we will use. Now you'll see that the total number of rooms have such, it varies from a completely different scale, and some of these are not even the uniform distribution, they are tail heavy, they need to have more bell shaped distribution, right? So after further looking into this, we will try to go into the visualization part of it. I'm going to skip this part for the time being. Mm, yeah. So the another thing that we do is we look at the median income and we sort of put it into the bins. We make a categorical variable. This is what we are mostly doing for the visualization purposes. So I'll go directly to the visualization. So here you will see I have plotted the scatter plot, which has longitude, latitude as x and y, and every dot represents one row, right? So if you will see this example, does it give us a lot of information other than that there are a lot of dots along this side? It doesn't, right? It doesn't tell me anything about the prices of the house. It doesn't tell me that whether most of the houses are located here or they located here. What is the difference? So this is not a very good visualization. So we can definitely develop a better visualization, right? For example, if we'll come here, you will see that I'll just change the value of the alpha, which helps us to see where most of the houses are located. We can see that these places are more densely populated as compared to the other places which are shown by the lighter color of dots. So it gives us some insight, some information about it, right? Now let's try to make it more full of information. So we can maybe change the size of these dots, we can change the colors of these dots, right? Let's try to do both. So in this case what we do is, so this is again the same scatter plot. Nothing has changed here, right? The same houses, if you will see the same longitude and latitude. But now what kind of information it gives us? With the different colors, we have represented the median house value, right? And with the different sizes, we have represented the population. So bigger the size of the circle, higher the population of that block is, and more reddish sort of a color, it means more expensive, like the price of the houses. This is the median value, house value in that district. So if you will see that most of the expensive houses are located around this region, right? This is the kind of insight that it provides us. But these are relatively towards the one with the blue ones, they are a bit towards the inexpensive side or on the lower end of the prices. So what is the difference? How do we know that? What's special about these houses? So maybe the next step what we can do is, I have tried to put the map on top of these problems. I have tried to put the map of the California. So you will see that the expensive houses, they are around the beach, right? These are the houses which fetch more price because people want beautiful beach views, like closer to the beach with the so that's why these houses are more expensive. Or maybe there is a chunk of houses here also which have bit of a cost in itself. So so now this is a good visualization. This is something that we, when we try to explore our data, the one of the first steps that we do, can we visualize it? Can we visualize it in a better way? The next step is we try to derive more insights from it, looking at the correlations or the other statistics of it. So what we are doing next is we are trying to look at how the median housing value varies with all the different variables that we had, right? Like we saw, one of the variable, it totally correlates it with is the its location. We had ocean proximity, so the houses which are closer to the ocean, the housing price has some sort of correlation to it. So let's see if it has correlationship with the other variables as well or not. So let's say we see that the first variable with which it has the highest correlation is the medium income. What is the medium income of the people in that block or the district? So higher the income, it means more money they can pay, and higher the value of the house will be. Now what is the, like, the total number of rooms? Then there is the median age, then there is number of households in that area, total number of bedrooms, and it is negatively correlated with the population. Maybe more densely populated the area is, lower will be the value of the house. So the next, we will try to visualize these correlations itself as well. So this is something that we call as the scatter matrix plot. which helps us to see what is the relationship between the different variables. For example, this is the median housing value. You will see that with the median income, it has a very good sort of a positive correlation. You will see, like with the increase in median income, the housing value also increases. Similarly, you will see that the like this is the one that we have already seen, but the rest we do not see. Like we see that with increase in this, there is a with increase in total number of rooms, there is total, somehow that is correlated with the median income as well. But the correlation that we see between the median housing value and the median income, that is very good. So these kind of visualizations helps us to understand. This is somewhere we have, because we figured out that this is the one that shows us the best correlation. So we will look more into it. We will dive deeper into this. Now, the first thing that comes to our mind is, like, we have been looking at the rooms, total number of the rooms and the total number of households in that area as independent variables. Can we generate more information out of it? Can we make more variables out of it? Maybe, we can get the rooms per household, right? We can see what were the total number of rooms in that block, and how many households are there in that block, and we can get an estimate, an average of the rooms per household. Similarly, we can get an average, like we can get bedrooms per room or the population per household. This will like we can always generate more information from the existing information. So when we do that, we see, and we again look at the correlationships, we see there is a certain improvement. Like the room per household, it gives us a better idea than the total number of rooms in a block, right? So sometimes we need to perform these kind of operations as well on the before we go into the before we go into developing the machine learning algorithms, right? So these are again some more visualizations. Maybe I can skip that for you. Now, yes, so this was the part where we did the looked into the data, we did data visualization, we try to understand it more. Now the next step is how to build the machine learning algorithm on top of it, right? So before we develop a machine learning algorithm on top of it, we need to do the data cleaning. We did observe that some of the values, they were missing. For example, if you will look at the data here, you will see that for this particular uh, houses, we do not have information about the total number of bedrooms. We just do not know. We have NANs. So what do we do? What do we do when we get this kind of missing values? We need to figure out a solution for that. Now, there could be one alternative, that is we simply remove the total number of bedrooms as the variable, because we see that it has NANs, right? Or we can drop the rows corresponding to which it had NANs and keep those rows where it had certain values. Or the third option could be that we choose and that we substitute these NANs maybe with zeros, or with the mean value, or with the median value, right? So there could be a couple of options, and we can try which one works better for us, or we can try it on the or we can make a choice on the basis of the resources that we have available, right? So let's say option number one, we decide to completely drop the total number of the bedrooms, and similarly we drop the total number of the we decide to drop the total number of, like, the rows itself. And the purpose here to show you all this is that it is not very difficult, in the sense that using Python, it is only a matter of one line where we have to write drop NA, and we want to tell them, like, this is the column on the basis of which we want to drop it, right? Or, like, if we tell them drop, like if we set the axis is equal to 1, it will drop the rows, not the columns. Or the third option, where we replace it with some sort of values, where we have replaced NANs with, in this case here, 433, which was the median value, right? So these are the different sort of strategies that we use. Now the next thing is, as we observed, all of our variables, these are continuous in nature, but there is one which is ocean proximity, and it is categorical in nature, right? So we have to convert this one into the we have to convert this categorical variable into into a numerical one, right? Into, sorry, yeah. So we need to convert it into a numerical value. So how do we do this? Again, there could be multiple options to do that here. So just before I go ahead, wanted to take some feedback. If you would like me to switch to the slides, I can do that. If you find it a little difficult to go through the codes, I have also like prepared the slides corresponding to it. So if you prefer this, please let me know if the code somehow confuses you, or if you're not familiar with the language. So we were talking about the machine learning pipeline, that before we develop the algorithm, before we train our algorithm, we need to perform certain set of pre-processing steps. The very first one, that is the data cleaning. We will look into the, like, we will first separate predictors and the label, that is X and Y. We will look into the missing values. We saw how we can perform different sort of we can take different approaches. For example, we can delete that attribute altogether, that column altogether, or we can get rid of the some of the rows where the values are missing, or we can replace them with the zero value or the mean or the median. So the next thing is handling of categorical variable. For example, we saw there was one variable known as ocean proximity, right? And that variable had 5 different attributes. Now with the ML algorithms, the one of the steps is that we need to either drop the categorical variable, but if that's not the case and if it provides good information, then the next thing is we need to somehow convert that categorical variable into the numbers, convert somehow text into the numbers. Now there could be different approaches. One of the approach which we call, it is called the ordinal encoding. In this case, what we do is, for example, if this is your variable breakfast, every day, never, rarely, most days, never, these are some of the values that it has. We can replace it with the integers. We can replace it with let's say the never was labeled as 0, then rarely was labeled as 1, most days as 2, and every day as 3. But there is a problem in this case also. Here it might, I have chosen this very specific case because here it might make sense, because if we talk about the order, then maybe the never like comes before rarely, or if I go the other way, then rarely comes after never, most days comes after rarely, and then every day comes after most days, right? So there is an order to the variable. But then in many of the variables, there is no order to the levels that there are. For example, if I talk about, let's say, gender, male, female, third gender, now what is the order? Is there any order? No. So it creates the problem of distance for us over there. So it is not always advisable to just replace it with the numbers, just replace it with the ordinal encoding. So the another approach that we can use in this case, for example, I have it over here. It is called the one hot encoding. Now, in this case, you will see that the variable had the values red, yellow, green. Now, as I said, there is no order to it. Can we say that red is superior than yellow or green is better than red? There is no such kind of order in there, right? So using the ordinal encoding is not our first choice. It is not something that we will prefer. So we will go with the one hot encoding itself. In the one hot encoding, the what we do is, instead of one column, we end up creating more number of columns, which is equivalent to the number of levels we had. For example, if it had 3 levels, red, yellow and green, we created 3 columns with the name red, yellow and green, and the and where its value is red, that is labeled as 1, and the rest, the values are put as 0. Similarly, if you will see, the third column had the value which was yellow, so we had put 1 over here, and rest of them are 0. Now this is called the one hot encoding. It comes with its advantages, but at the same time it comes with its disadvantages as well. Let's say if you have the number of levels are a lot, instead of 3 colors you have 30 colors or 300 colors or a lot of them, then using such kind of one hot encoding, it may result in a very sparse matrix, a matrix which is full of zeros, which in itself may become a problem for our algorithm, right? So we don't even want that in all the cases. So whenever you perform such kind, whenever you handle categorical variable, you have to ensure that these kind of problems are not, you have to ensure how many levels are there, what does those level means. As a designer, you have to look into these different aspects of it. Then the next thing which is very important is the feature scaling. As we saw in this very particular example itself, that most of the features, they are on different scale, right? Some varies from sorry, just maybe I'll switch to the code. Or anyways, we have discussed this earlier. So they have different scales. For example, we saw income was in thousands, the total, the number of bedrooms per household, it was in tens. So the machine learning algorithms do not perform very well when when the inputs have such varied range. So there are a couple of different approaches that we do. The first one is we scale it between 0 and 1. So whatever the input, we just simply do a linear transformation, and we say that, let's say if it was from 1 to 1000, so we will accordingly scale it to the 0 to the 1, where the minimum value will be the 0 and the highest will be the 1, or any other range that we may like. It has a disadvantage that it is affected by outliers a lot. Let's say that there was only one variable where let's say there was only one level with the value 1000, rest of them, all of them were between 1 to 100. So the same, when we will downscale it to 0 to the 1, the same will happen over there as well. So this kind of scaling is very much affected by the outliers. Then the second is the problem of second is the standardization, where what we do is we we normalize it so that its mean is 0 and the standard deviation is equal to 1, where we subtract all the values of a variable by its mean and divide it by its standard deviation. It is generally not very much affected by the outliers, and it also does not bound the problem, for example, into 0 to 1, which sometimes may be a problem for the some of the algorithms, right? So it gives us that sort of flexibility as well. So these are generally the most used feature scaling that we use on our variable. And remember that we are doing it individually for every variable. It like the number of bedrooms will have a different scaling, and the number of let's say the total number of the rooms, they will have a different value of the scaling. It will not change. We do not look into consideration the relationship between them. Now going back to the codes itself, yeah, so that's what we have done for the for our variable as well. Like one is the we had this ocean proximity variable, so we can drop it, or we can replace it with the mean, or we can impute it. So I'll show you just in I'm sorry, I'm skipping all of these parts so as not to confuse you. Yeah. So this is here, like as I was talking about the encoding part, this is where we have encoded it into the one hot encoding. As you can see that it has one where that value was correspondingly had a value, and rest of the places we have put a 0. This was done with the ocean proximity variable in itself. So, for example, okay. So, what I'll do next is uh, maybe I'll skip these codes. What I'll do next is we will now switch to the linear regression PPT itself, because that's what our next step is. Like in this case, we want to build an algorithm. Now it's a linear regression problem. I hope that's obvious by now, right? Where we want to predict the price based on the input variables. For example, here we have shown the area. So we will now see how the linear regression in itself works, and then we will switch to the codes that how to train a linear regression model in the how to train linear regression model in Python itself, right? So I'll just share the another set of slides with you. Yeah. Can you see my slides? So before we go into the mathematics of linear regression or we see how it works, I'll just give you a few examples. And let's say we have this data where x1 and x2 are the inputs, whereas y is our output. So, and these are the data points we have. We have 4 data points. Can you tell me what will be the relationship between x and the y? I mean, it's a very simple thing. If you will look at the input and then if you look at the output, you can tell what is the relationship. Okay. So if you will see that output y, it is simply the sum of x1 and x2, right? Y is equal to x1 plus x2. Or if I write it something like this, y is equal to 1 into x1 plus 1 into x2. Similarly, if I look at the another data here, and if we try to look at the relationship between x and y, it will come out to be something like this. Y is equal to x1 plus 2 into x2. We can see that, right? 1 plus 2 into 1, it will come out to be 3. 1 plus 2 into 3 will come out to be 8. So that's the relationship between the input and your output. Similarly, if we have, let's say now 3 different variables, and if we try to look at the relationship, we can also find out that. But if I want to generalize this, if I want to generalize this equation, can I simply write it as y is equal to some theta 1 x1 plus theta 2 x2 plus theta 3 x3, right? Because when the number of variables will increase, so this is like the generic mathematical notation that we will be using to describe the relationship between input and the output. And if you understand this, this is what the basic of linear regression is. This is where you will understand that the whole purpose of linear regression is to find out these values of thetas, which will set up a relationship between your input and output, and finding and how to find those theta values, how to fine tune your algorithm to get the best theta values. That's what the whole linear regression is about. Now you can say that if it is so simple getting the relationship between input and output, then why do we really need a machine learning algorithm? I can just look into the data and then say, okay, this is the relationship, this is simply a line, right? But this problem becomes very complicated when you have many different variables. When you have variables, maybe you have hundreds of variables, can you do it manually? No. When your data set becomes bigger, instead of, let's say, 4 rows, you have 40, you have 400, you have 40,000. What you do in that case? In that case, we need a mathematical function, we need an algorithm to look into the patterns and tell us what is the relationship between your input output, to tell us what are the optimal parameters of these theta 1, theta 2, theta 3, theta n, for that matter, if we have n number of variables. So if I simply talk about regression, this is how simple it is. You have certain training data set, we develop a learning algorithm on top of it given the x and the y, and we find out the hypothesis. By here hypothesis we mean, again, h of theta, which is equal to theta 1 x1 plus theta 2 x3 till theta n xn, and the optimal values of theta. That's what our hypothesis is, which lets us know the relationship between input and output, right? And here our output is a real valued output. So as we saw in our case, let's say for the time being, just for the simplification, instead of having 9 different input variables, I'm only considering one. Let's say I'm only considering size of the house and the output as the estimated price that we want to find out, right? So when I go further, this is how the single input variable. Now we are talking about univariate linear regression, and then we will move to the multivariate for the purpose of understanding, and we will come back to our data set in Python that we had seen. So here you see again a scatter plot which tells us about the, like, whatever the high size of houses and its actual price. Now you can see that we have certain data points here which are marked by these crosses. Now, what we need to understand is, let's say I want to know what will be the price of the house if the size is around 1,000. So, but unfortunately, we do not have any data point here corresponding to, sorry, the line is a little, let me try to make a better one. But unfortunately, we do not have any data point that tells us what will be it price, right? Similarly, if I want to know what will be the house of the what will be the price of the house if the size is around 3000, I do not have any data point. So what do I need? I need a certain relationship between my input and output, which I want to draw on the basis of these data points. And I can see that with increase in the size, the prices are also increasing. So we can expect something like this, right? So this is what we want to find out. This is what you can say in we want to find out this line, and the whole regression is around it. So if I put this instead of the visual, if I again put it in the form of the data and introduce more notation to you. So let's say this is our data input, output. Input we are representing by X, output we are representing by Y. M is the total number of examples that we have. Like let's say the total number of houses that we have. In this case, let's say the M is 47. Then one training example is represented by XY. If I want to, let's say, very clearly mention the example number 1 or 2 or 3, we will use the superscript here, XI and Y of I, to represent the ith training example. For example, X of 1 will become 2104, right? Similarly, X of 4 will become 852. So this is the notation, and if there is any confusion regarding this notation, please let me know, because we are going to use it in the next slides as well. It's not very complicated. XY as input output, M is the total number of examples, and to represent the training example, we are using the I as a superscript. So this is our model representation. We have a training set, learning algorithm, right? And we want to find out our hypothesis, which gives us the relationship between size of house and the estimate prices. So as I showed you in the very first slide of the linear regression, this is what we want to find out. And in the generic terms, we will write it. Right now we have only one input, so we'll write it as theta 0 plus theta 1 x1. So you might be aware of this. This is the equation of the line, right? And we are writing this equation as hypothesis, h of theta of x or h of x. So yeah, so this is our univariate linear regression, and this line here, that's what we called h of x. Now the next thing is the cost function. How do we find this line, right? So that's somewhere we will go next. Now we know that in generic, in mathematical terms, we are writing as h of x is equal to theta 0 plus theta 1. Now this is something that we want to find out. These are the parameters that we want to find out to see what is the relationship between input and output, that how this output is related to this thing, right? So how do we choose these thetas? And these are very important. Now I'm putting in front of you some very simple examples again, right? For example, let's say again a simple line theta 0 theta 1 x. If we put the value of theta 0 as 0 and theta 1 as 1.5, right? Then for the different values of x, what kind of line we will get? For example, when x is equal to 0, it will be somewhere over here. It will again be 0. When x is equal to 1, it will be somewhere, sorry, I have put it a bit opposite. Theta 0 as 1.5, and sorry, the line which I have made is a different line. Yeah, theta 0 as 1.5, and theta 1 as 0, right? So when theta 1 is equal to 0, what does this mean? Irrespective of the values of x, it will always be equal to theta 0, which is in this case 1.5. So this will come out to be our line, right? So let's say if we change the values of theta, we keep this theta 0 as 0 and theta 1 as 0.5. Then what will become? When the value of x is equal to 1, the value of y will become 0.5, right? When the value of x is equal to 2, the value of y will become, what will be 0.5 into 2? 1, right? So this is how this line will look like. This is how the relationship between x and y, or a hypothesis line will look like. So you can see how changing the values of theta is changing the relationship, right? So let's say if theta 0 is equal to 1 and theta 1 is 0.5, then we get something like this. Here you will see we are also getting a certain intercept, that irrespective of the value of the x, we'll have at least this much value of the y. Sometimes we also call it as bias, right? So it is important for us to find out. Now, how do we do this in our case, right? This is something that we want to find out, but what does this line means? We want to find out a line which can represent our data as clearly, but in this case we see that this was our actual data, but this is what our algorithm had predicted. This is the line, right? This is the relationship that we got between x and y as per our hypothesis. So how much of error will be there? This is the error that we have got. And similarly, we have certain set of error for the other data points as well. Maybe in this case we do not have any error. Now, our objective is to find out those values of thetas, to find out that hypothesis, that line, which will result in minimization of these errors. Let's say if instead of this blue line, I would have, let's say instead of this line, we will go with something like this, right? Sorry, it's not a straight line. Then in this case, you will see that the errors are actually quite a lot, right? The errors between what you will predict and what actual data says, these will be quite a lot. So this will not be a very good fit. So we want something which will help us to minimizing these errors, which in this case are the vertical distances. So if I want to write this thing mathematically, how will I write it? Now here h theta x of I, actually, like this represents every example, minus, so this is your predicted value minus your true value. uh, so if I, let's say if I take this point, right, so its predicted value will be somewhere around here, whereas its actual value is somewhere around here, right? Predicted value might come out to be maybe 110 and actual value is, let's say, 100. So what will it become? Okay, so so that will yeah. So what was the predicted value? Let's say 110, and then your actual value was 100. So we will take the difference between these two. We will then do a square of this, and we will sum it over all the examples. That means that we will take it over all the other examples. We will take all of these differences. Let's say the predicted value is 200 and the actual value is 300, so it will come out to be 100, right? And so on. We will do it over all the examples, and then we take the average out of it. So this is something that we want to minimize. This becomes our function. Here remember that h of theta x is what we found as theta 0 plus theta 1 x1, which was our hypothesis line. Now, so this is how we write our objective function by j of theta 0 and theta 1, because it is a function of this theta 0 and theta 1. Like these thetas, these parameter values will determine which line we will have. We'll have this, or we will have this optimal one, or we'll have something like this, right? Which will further in turn tell us how much errors we will have, if we will have this much of error or if we will have this much of error. So this is our objective function which we want to minimize in order to find out the optimal values of theta. This is what we call as our cost function. So if you will see here, in the one dimension, like we had one input, one output, this is how your errors will look like. But if you have two inputs, let's say, and one output, so this is a plane. So I have just put this figure here so it will help you to visualize how these errors will look like in the 2D domain as well, where you have more than one input. Like we cannot visualize it for like three input variables. That's our extent of visualization. But this is how it will look like. Now, the thing here, we have seen our hypothesis, our parameters that we want to optimize. This is our cost function, and this is the goal that we have. We have to minimize this cost function. For the time being, what we will do is we will simplify it, right? We will only assume that we have theta 1x. We will, for the time being, assume, ignore theta 0. We'll set its value equal to 0. We are just doing it for the simplification process so we can understand the mathematics behind it. Later on, we will realize that even including theta 0 doesn't make difference. It's the same. We have to treat it in the same way, right? So our parameter is theta 1, and then our cost function is again this thing, and we have to minimize it, but we only have theta 1 now, right? So now what does this really mean? So let's say this is our data now. You can see this is x, this is y, and if you will just see it, you will see when the value of x is 1, output is 1. It's a very simple straight line. Y is equal to x, right? So this is the optimal value, we can say. So what is the meaning of y is equal to x? Let's say our hypothesis h of x, sorry for this, it will come out to be uh, simply 1 into x, right? Where 1 is the value of theta 1. So if I correspondingly plot the value of theta 1 and plot the value of j of theta 1, which is our cost function, you will see that when the value of theta 1 was 1, the error is actually 0, right? It's a perfect fit. But what if we choose a different value of theta? What if we choose the value of theta 1 is equal to 0? Then what our equation will become? Y is equal to zero point 0.5 of x, right? So these are the values, and our errors will become higher. So we will see that when our value was 1, our hypothesis predicted its value as zero point 0.5, because we have set the value of theta 1 as zero point 0.5. And then at when x was 2, the predicted actual value was 2, but our hypothesis gave us the value of 1, and similarly for the third data point. So our error comes out to be around somewhere around 0.58. So when our theta 1 was around here, our value, our error was around zero point 0.5. Now similarly, let's experiment with another value of theta. Let's say the value of theta we have set equal to the 0. So this is what our line will become. Y is equal to x. It means y is equal to like theta 1 into x. Theta is 0. So it will come out to be simply a 0 line. All of this will become our error. Our error will become this huge, right? It will come somewhere around here. Similarly, if we will plot more equations, more hypotheses, we will see that the cost function will look something like this, like a parabola convex function. And our objective is to find this optimal value of theta, which will give us the minimum error. If not 0, the minimum one. And our problem becomes simpler because it comes out to be a convex function, right? So if you will see here, you might have studied, the different computation numerical optimization techniques, and this parabola might remind you of something like that. Might have heard of the gradient descent. So we will talk about that how do we find the optimal value of theta in order to minimize this thing. So I hope by now you understand how this line, our data, and the cost function correspond to each other, right? So this is our hypothesis, these are our parameters, our cost function, and our this is our goal, right? So in more than one dimension, like when we have theta 0 and theta 1, our cost function will look something like this, and we'll have to find something. This is simply the extension over the two dimensions. Okay, right? So now let's say, coming to our housing data set. So input our size and output is price y. This thing represents our data points. Now let's say I set a certain value of theta 1 and theta 2, which gives me this equation of line. Now do you think this is a good hypothesis? No, right? And the correspondingly in the theta 0 theta 1 curve, it will give me somewhere around here. You will see this is a contour plot of the same parabola that we have seen here. If you will see this one from the top, right, from if you will look at it from the top, it will look something like this. So our objective is to reach here, is to reach at the point where we have minimum cost, right? So maybe when I tried it with this thing, it's not a very good fit. What do we want? We want this line, we want to reach here. So in order to reach here, we need to find out the good values of theta 1 and theta 2, and this is where the gradient descent comes into picture, right? The how the gradient descent works now. um, okay, so maybe we will start from here. Yeah, so how gradient descent works, let's say what we do is we first start from some random point. Let's say I'm not following this contour, I'm following some other contour. Let's say we are somewhere over here, right? That's where we start. We just randomly initialize. Let's say we just initialize our theta 1 theta 2 to be equal to zero point 0.2 zero point 0.6, some random value, because we have to start from somewhere. And on the contour plot, it gives me, like on our cost function plot, we are somewhere over here. In order to reach the minimum value, what do you think we do? Now imagine it at some sort of a valley. In order to reach at the bottom of the valley, now you may have multiple options, but what will be the fastest way? That you may look at the slope which is the steepest, right? That may help you reach there the fastest. So we need to find out. Now from this point we can go to the several different directions, right? But we want to go in the direction where we get the maximum this thing maximum slope, where we get the maximum gradient, and we want to descend in that direction. That's why it's called the gradient descent algorithm. So this one contour here shows the different steps. Let's say we start over here, in the next step we reach there, in the next step we reach there, and so on, and then we find the optimal value over somewhere around here, and these will be the values of theta 1 and theta 2 that we want to find out. So if I just simply talk about gradient descent, very simply it is start with some value of theta 1 theta 2, keep changing the values, right, to reduce this thing until we hopefully end up at the minimum. Now again, coming back to the one dimensional thing itself. So when I talk about the gradient descent, so this is you initialize, and since we were talking about the gradients, the new value of theta will be equal to previous value minus alpha, which is the learning rate. We'll talk about this alpha in just a minute, into the gradient. This gradient will decide which direction we will take and how steep we will take it. For example, if now again we are coming to a cost function which is which depends on this one value of the theta. Let's say we were somewhere around here, right? We This is our cost function. We want to move in the direction which will help us to reduce the value of theta. So we will go in this. We will not move in this direction per se, right? And the step that we will take, that is called the learning rate alpha here. It will decide how much we want, like how big of a step we will take. If the alpha is small, maybe it will be just here. If the alpha is very big, it will be like this, right? So this is what the gradient descent is, and this is as simple as this is. We start from some point, then we move, we go ahead to the next point, then we again update, we move to the next point, then we again update, we move to the next point till we reach the bottom, till we get our optimal values. So gradient descent, repeat till convergence, where theta is equal to theta, where theta j is equal to theta j minus alpha into the differential gradient. And remember, this will be done with respect to the theta's value that you want to find out. If it is theta 0, then it will come out to be theta 0. If it is theta 1, then it will be with respect to the, like the derivative will be with respect to the theta 1. And this is what defines a rate of change, and alpha defines a step size. So this is if you want to go with both theta 0 and theta 1s. So let's once again see this gradient descent algorithm. So if you will see here, let's say we start at this point, right? Then we look at the slope. What will be the slope at this point, which is generally done by taking a small, like small increment in the value of theta, right? We generally do it in both the directions. Then we find out where we have to move, and let's say if we start from here, this is the direction it will go. If we'll start from here, then this is the direction it will go, right? So it also depends upon where you are starting from. But it will go towards the direction of the minimum, it will go towards the this thing, the minima. So if you're around here, our gradient value, it will be positive, it will be greater than 0. But if you are around in this region, our gradient value will comes out to be equal to negative, which would mean that, let's say, if you are in this region, our gradient will come out to be negative. Sorry, I'm sorry, the our gradient will is positive, right? So it means we are ultimately decreasing the value of theta, because here we have a negative sign. So the next value of theta will be somewhere around here. But at the same time, if we start from here, our gradient will come out to be negative, right? So the negative negative becomes positive, which means that we will end up increasing the value of theta. So maybe earlier we were at 1, now it will become come out to be 1.2 or something, but ultimately we are reaching over here. That's our ultimate goal. And this is mostly how the gradient descent works. The very important parameter here is learning rate. If we set the learning rate to be very high, there is a chance the algorithm may never converge. Let's say we start from here, but we add a very big value to it, right? Like when we add, we move towards this direction, right? But instead of coming here, we kept the learning rate so big that we jumped to this position altogether. And then again, when we have to go back, now here the gradient was this thing, so we have to go back in this direction, but again the learning rate was so high, instead of coming down here, it may simply switch over there, and this process will keep on going on, and we will never reach our optimal value, and our algorithm will divert. So it is important that we keep the learning rate small, but at the same time, very small learning rate means it will take very short steps, and it may take a very long time to converge as well. So we'll have to sort of fine tune the value of the learning rate in itself in this algorithm. So again, coming here, I hope this is clear now. The gradient descent for linear regression, where repeat until the convergence, theta is equal to, again, theta minus alpha into the value of the gradient, right? Where our h of x is equal to theta 0 plus theta 1 x1, and this j of theta is this one, our cost function, which we have already worked with. So maybe I will skip going into the details of how do we compute the partial derivatives. I'll just show you the final output. This is how it will look like. When we will take the gradient, it will come out to be something like this. So this is the equation that we just used. In order to update theta 0, theta 1, and theta n, we subtract the previous value of theta with alpha into averaging it over m examples, and it comes out to be like your predicted value minus your actual value into your input, right? So this is how your final equation for updating the theta values look like. And this is more or less all the variables. So if you will look carefully here, uh, I've shown that, like, it starts somewhere over here. We keep on updating the value of theta till we find out this optimal value. So this is how the gradient descent really works. And this is our aim to get that. Now, what we had seen was we use one example, right? And then we are taking the average over this. So this is batch, where each step uses all the training examples. Now this is like in the very beginning of the presentation, in the previous lecture, actually I talked about batch learning, right? Where we, for training the algorithm, we use all of them at once. So this is what it means, that we are taking all of the examples in one go. What we do is, in one iteration, we take the actual minus predicted minus actual value, and we, for all the examples, and then we take the average, then we update the values of thetas. But then there is another possibility, where what we do is we update the value of theta based on every single example. We do not update, let's say we have taken this one example, we update the value of theta, then we again take the next example, we again update the value of theta. So it's like getting a new line, getting a new this thing for every for every data point. So that's what the iterations are in the case of online learning. Now there are a couple of other features that we can look into. For example, uh, let's say we have, now we talked about univariate. What if we have multiple features? We have size, we have number of bedrooms, number of floors, age of the home, as we have seen in that data set, right? So in this case, again, one you have to understand is the representation, the mathematical notation. Now, where m represented number of examples, n is the number of features, and xi, it represented, if you remember, the ith training example. Here, the J subscript will be used to describe the value of the feature. For example, x3 of 2. What will that become? If you will see that 2 here means second example, right? So 1, 4, 1. It means this second row. And third feature would become this thing, x3. So its value will come out to be 2. Similarly, x3 of like if we look at the fourth example, its value will come out to be 1. So this is the notation that we use in case of the multivariate. So this is what we had previously, this is what we have now. It's not difficult, it's the same. It's just that we have expanded, we have gone beyond theta 0, theta 1, we have come till theta 2, theta 3, theta 4 as well, with the more number of variables. But the mathematical treatment will exactly remain the same, the gradient descent will remain the same, right? Just for the simplification, what we do is we sort of try to represent it in the matrix form. So this is our hypothesis. So let's say we represent our input x by a vector, a column vector, x0, x1, x2, x3. And similarly, we represent our thetas as another column vector as theta 0, theta 1, theta 2, theta till theta n. So we can represent our hypothesis as theta transpose x. See, it's still the same, nothing has changed. It's just that writing this way is more sometimes computationally efficient. It helps us in better implementation without going through all the loops. So also easier to understand. So this is what our hypothesis becomes like. So that's what we have seen before, right? With the new thing, nothing has changed. It's the same equation, same this thing, we just generalize it. Instead of writing theta 0, theta 1, we are writing theta j. The equation is the same, exactly is the same. Your algorithm will work exactly in the same manner, right? Now, there are a couple of problems that happen in the gradient descent. If you remember, uh, I talked about the scaling of the features, where the number of bedrooms will have a completely different range than the age of the house, which may only vary till 40. So when we have different sort of scaling, different, then the contour plot will look like this. It becomes difficult for our gradient descent to to find out the parameter. It actually slows down the whole process. So what we do is, as I showed you, that we can scale it between 0 to 1, or let's say -1 to 1, or we can use the standardization scaling so that it becomes similar in all the directions, and it becomes easier for our gradient descent to find out the optimal value. So this is where the importance of feature scaling is. We are doing it so that our learning algorithm can work better, can work more efficiently, right? So yeah. Sorry. Hmm. Yeah, so this one here, it shows you with the number of iterations or epochs in this case, because it's a batch learning. It will show you how the different learning rates will impact your cost function. So if the learning rate is very high, instead of converging, it may just diverge. Your cost will keep on increasing with increase in iterations. So that's actually a signal for you that we do not want to have such a high value of learning rate, such high value of alpha, because setting its optimal value is very important. So generally, what we do is we try different values of alpha and observe its curve. If it is very high, you will see a diverging sort of behavior. If it is low learning rate, you will see that the loss is decreasing with respect to time, but at the same, this convergence might be very it might be very low, right? I mean, you will not see that kind of steep rate. If we further increase, let's say, the value of the alpha, you may see that this could be the example of the good learning rate, where it is decreasing, and like it has helped us achieve the minimum error as well. Again, this could also be where there is a high learning rate. It has decreased towards certain, and then after it has almost become stagnant. So your purpose is to find out the learning rate, to find out the value of alpha, which gives you this kind of curve, right? Neither diverging, not too slow, not something that becomes stagnant. This is what our goal is. This is how we set the value of the learning rate. So now again, coming back to the this thing, our house pricing prediction. So what we have done is, we have taken now two features, like the depth and its whatever its front area is. Like the area, we have divided it into the two parts, and we have taken its length and width, you can simply say, right? The frontage and the depth. So in this case, this is our hypothesis. Now what I want to show you here is that sometimes what we can do is, we can, instead of just using the features like x1, x2, x3 and something, like instead of simply using our features, we can create more features. Like I showed you one of the example where we divided the total number of the bedrooms divided by total number of households. Now this is another example where, let's say, my feature is x1. I can also take the square of it, the square of it as well as its cube, right? And create a new feature out of it, and then treat it in the same way as we have a new feature. So we will write this line: h of x is equal to theta 0 plus theta 1 x1 plus theta 2 x3 plus theta 3 x3, right? So do not think that it becomes like the polynomial in the nature, because we have taken it as still a sort of, you can say it is still a linear relationship between the input and the output. It is still a linear regression. By polynomial here we mean that the input values, we are taking a certain polynomial of it. We are taking squares or cubes or something of that. Sometimes these kind of approaches also helps us to achieve better performance. So that's something that we can do. So now the linear regression, we have learned the way of, using the gradient descent, which is an iterative algorithm. We start with something, then we update the value of theta, then we again calculate the cost function, we see if there is an improvement, then we again update the value of theta based on that improvement, and we will keep on doing this till there is a convergence. But there is another method as well, which is known as the normal equations, where we simply use the matrix operations to find out the optimal values of theta. This was also one of the purpose to introduce the notation of theta transpose x. So let's say here this is our data set, right? So we have simply represented it in the form of x, which is now a two-dimensional vector, where the rows define the examples, and the columns define the your variables, your feature set, and while that is your output. In the sense, here it is the predicted value of the price. So what we can do here is, in order to calculate the value of theta, now this equation we have come to after a lot of mathematical this thing. So I will again, I'm not showing you the details here, but this also gives you the optimal value, which is x transpose x. Then again you take the inverse of whole thing, again x transpose into y. So this is the another method. If you do not want to use gradient descent, this is the another method by which you can calculate the optimal values of theta. The disadvantage is, if your data set is very big, let's say the dimension of the x becomes very big. It is, I don't know, you have 100,000, 1 lakh examples, and 100 features, then the multiplication operations, it may require a lot of computational power and the resources. In that case, maybe going with gradient descent is a better option. But the advantage of using this kind of equation is that it gives us only a unique solution, whereas with gradient descent, depending upon where we start, we may get different solutions at the different time, right? So I think I will not go further into the details of the probabilistic interpretation and everything. This is where I will stop with the theory of linear regression. A couple of steps that we have already talked about. Maybe I'll show you the. Just 1 minute. Yeah. So we have seen almost, yeah, like almost all of the steps of this thing, like looking at the big picture: data collection, visualization, data discovery, data preparation, where we did the scaling and everything. Now we are on to this part, which is model selection and training, fine tuning the model, solution representation, then launch, monitor, and maintain your system, right? So when we talk about model selection and training, in this case, now we know it is a regression problem, so we have to use a regression variable, right? So what we do is we develop, let's say, a model. Yeah. And in order to select which model performs better, we set up a cross validation pipeline. Now, what does that mean is we have a whole data set. We split that data set into two parts. We split it into the test data set and the train data set. Now, train data set is the one that we will use for the training purposes. And the test we will keep completely separate. It's like an unknown data set, something that the algorithm has never seen before. So what is the purpose of this thing is it helps us to understand if our algorithm is overfitting on the data set or if it is underfitting. We need to know how well it will perform on the unknown data set, right? So there are different sort of cross validation methodologies as well, not go into the details. So the approach generally that we do is we split the data set, set up the cross validation pipeline, then we try different algorithms, and then we also try to fine tune the different parameters of those algorithms. For example, in the linear regression, there is the value of alpha, right? And after we do that, we will launch and we'll deploy our algorithm, right? Because models, they tend to rot as data evolves over time unless they are regularly trained on the fresh data. So we also plug human evaluation pipeline into the system. So we train the model regularly on using fresh data and we automate this process. Now I'll show you some of the codes that we have here. Uh, so if you will see here, this visualization again tells you that if your learning rate is very fast, this is how it will keep on diverging. It will not converge. And if your learning rate is too slow, it may take a very long time to reach the optimal value. And you may actually stop your algorithm before it reaches there. And this one just shows uh, the number of like cost function with respect to the iterations. So yes, so now coming to the linear regression part of it. So what we have to understand here, in order to use the machine learning algorithms in Python, there is a library called as sklearn. From this library, we import the linear regression function from here, right? And in order to initialize it, it's very simple to use these kind of libraries. We simply tell them like it is a linear regression model that we are, and we define this object here. And in order to train our algorithm, we use this like dot fit sort of method that we use. We give it input variable, which is x, and we give it the output variable, which is y. In this case, our housing labels, right? And then by using this fit, it will train our algorithm. So maybe we can run this. Since it is a very small data, it doesn't take much of a time to run this algorithm here. Now, in order to predict it on the new data set, what we do is we simply have to write linear, again, like the object that we have defined there, dot predict, and we give it whatever the input data we have, right? Whatever the unknown data sample, and it will give us our output predictions. Like in this case, I gave this thing, 5 examples. So maybe I can show you that. So if we look at this thing, I'm only giving randomly 5 input examples to this. So, and we want to see what will be the value of the houses for these five examples. So we simply predict it with our trained algorithm by inputting this data, and it is very simple as writing like some data, like whatever we have done prepared along with it, and these are the correspondingly labeled. This is the output. This means that the first house, this one will cost around this 20 sorry 2,86,600 something. The next one will cost around this much. So in order to finally evaluate like how much of error we are getting, we use the mean square error that we have already seen. So we see what was the actual value, and then what is the something that we have predicted. So let's say here our prediction is known as the housing predictions, like we have put in underscore regress dot predict, and give input and give some data as input, we get our predictions. Then in order to calculate the mean square error, we give it the actual values as well as our predicted values, and it will give us the error. In this case, you will see that this is the error that it has given us, 68,000, which is actually pretty high. In this case, it may not be I mean very good, but also this is, as we say, this is better than nothing, but maybe clearly not a great score. And so maybe this is the example where we are underfitting our data. We do not provide good information to make the good predictions. So afterwards, I have tried different algorithms. I have not talked about it, but there is something called as the decision tree regressor also. From the point of view of implementation, it is also very simple and easy to use. Like again, from the sklearn library, we will import this function called as decision tree regressor. We will again initialize it. Then we will just again, this in the similar way we had used the linear regression, we will also use this one. We'll give it the input variables, we'll give it the corresponding output variables, we'll first fit it. After training the algorithm, we further try to predict it on the unknown data set. In this case here, we see that the error comes out to be around 0. But does it mean that our model is perfect? We have done a very good job? No, it does not mean that. Maybe it would mean that our model has overfit the data. So we do not want overfitting, nor we want the underfitting of the data set, right? So in that case, what we do is we try to fine tune our model. And in order to fine tune our model, as I was talking about, we split our data sets into training and testing, and we perform a cross validation on top of it. In this case, I have used a tenfold cross validation. Now, what does that mean is that um, we'll keep one part as test and rest of the 9 parts as the training data. So we'll split our data set into the 10 parts. We'll keep one part for the testing and rest of the 10 parts for the training. And we will do this with every chunk, holding out each of the chunk every time for the test data sets. And then we try to find out what are the values of this thing. So this is something that we have done over here. Uh, Maybe I'll skip the implementation part. Like there's a lot of implementation that I've done with the different algorithms. Also shown you how to like sort of use the grid search to find out the optimal parameters. For example, in the linear regression, we have learning rate as one of the parameters. So there's something called as grid search, where what it does is you give it the certain values of the alpha that you want to try on. Maybe let's say alpha is 0.01, 001, 1, 10, and so on. It will try it at all of those parameters and give you the best out and tell you which one has the least error or the best performance, and then you can pick out that algorithm in itself. So maybe I'll skip these details, otherwise it will get too much for one lecture. So if you have any queries, any questions, please feel free to ask. Maybe I'll show you probably the simplest method to start using the Python. So the one very good thing that we can do these days is use Google Colab. Google Colab has made our life very easy. You just go to this link. You can actually use examples, some of which have been provided, or you can create a new notebook. So once you do that, let it just load. Yeah. So you get all everything over here. So this will provide you a runtime environment. So Google has actually made it pretty easy where you do not have to download the different libraries, different this thing. So if you are a beginner, I would highly recommend that you simply go there and you can start using Python from here itself. Like let's say if you want to import different libraries, it is as simple as writing the code, and most of them are already there. If you want to import something new here, there is a command which is called pip. So you can do like pip install. Here I will not install it because it's quite a big library, but you can just like do OpenCV or something. If that one is already not in the environment, it will also come. So using Python has actually become very easy. Like let's say if I want to do 2 plus 2, it will tell me it is 4. Or if I also want to perform more complicated operations, and so I mean it is very easy that way. You can simply do it over here. Otherwise, if you want to go into a more formal way, like you want to install all the like environment locally into your machines, I would recommend using Anaconda. So you go to the website. It's simple. Just write Anaconda and Python. So what happens with this is this will give you a whole package which has Python, which has Jupyter Notebook, and a lot of different libraries which you generally need to this thing to run your algorithms or to work with. So if you want to do it locally, you can download this one. Otherwise, it's very simple with the Google Colab. Like even if you want to do sklearn library, which is mostly for the machine learning, you can just simply say export sklearn and then you can start using it. It's actually become very convenient these days to use all of this. Yeah. And I'll also highly recommend participants to maybe use Python, since it is open, like open access, free of cost. There's a lot of help which is also available. There is a very strong machine learning community which has built very good libraries. So this is a very good place to start if you want to start using machine learning algorithms.